PowerPoint? Yeah, I think so, right?
Yeah.
Perfect. Okay, I'm not even going to bother putting it in presenter view. Let's just do this thing. All right, welcome everybody to Chem 1B Exam 2 review session. Here's just like what we've covered up to this point, right? Just kind of like reel it all in. So chapter 15 was all about chemical equilibrium. So that was the first place that we saw like KEQs, equilibrium constants. Got introduced to the dreaded ice table. It's all right. It's really not. It's not that scary. Just own it. Own the ice table, and then it can't hurt you. We also saw in chapter 16, we saw acids and bases. And that chapter just kind of talked about like some definitions of what are acids and what are bases. Do we have strong acids versus weak base? We're strong versus weak, right? So strong completely dissociate, weak kind of sit kind of in the middle somewhere. We saw the autoionization of water and why that equation is kind of useful. The Kw value 1 times 10 to the negative 14th lets us kind of find Ka from Kb or Kb from Ka. We got introduced to two new, what seem like they're new equilibrium constants called Ka and Kb, but really they're just KEQ. All the Ks are the same. They just they give them different names depending on what kind of reaction they're being used to express, but whether you're looking at KEQ or Ka or Kb or KSP, it's all the same thing. It's all just the products divided by the reactants at equilibrium. So don't let all the different names confuse you. We saw some more ice table stuff with acids and bases. Chapter 17 then, we looked at aqueous ionic equilibrium, which is essentially like mostly about titrations, which are very difficult, so we'll go over some of that. And saw something called the common ion effect. And then we talked about solubility a little bit, like KSPs, just another way to express how much stuff there is present once a reaction comes to equilibrium. Same thing we've seen before. Um, with the gist being that previously we had learned that like things are, categorized as soluble or insoluble. But now it just broke it down and looked a little closer to say, it's not really that straightforward. There's actually a number associated with it. And you can really actually calculate just how soluble something truly is instead of just saying soluble versus insoluble. And then most recently, this week, and I guess last week too, was chapter 18, free energy and thermodynamics. So entropy, spontaneity, Gibbs free energy. And the way this is kind of going to work today is just I'm like, and if anybody ever has feedback about like what I cover or how I go over things, please let me know because I'm just trying to tailor this towards what helps you all the most. But what I was going to do is cover just like a couple points that I think will help overall with the exam, and then dive into like probably just some of the harder questions on the practice test, and we can go over those together, and I can give some explanations on those. Specifically, based on the kind of the input we got on the whiteboard on Friday, it looks like the newer stuff is pretty challenging. Maybe just because as we haven't had enough time, as much time to absorb it, and then titrations are just brutal always. So we'll go over. I'm definitely gonna go over titrations and then the newer stuff, free energy and thermodynamics. Do some sample problems. Cool. And if anybody, I can't really see the chat box when I'm doing this, but if anybody notices like comments or questions going unanswered, please feel free to just interrupt me and let me know that there's somebody asking something. Thank you in advance. All right. So first, I'll just try to talk about some like definitions and explain some of this most recent chapter, which is all about entropy, whether reactions are spontaneous or not, and ultimately Gibbs free energy, which just kind of puts it all together. All right. So just some like highlights from this chapter, I think. Uh, Firstly, I was just gonna say, if you've read the book, and I didn't see her lecture, so I don't know how much she focused on this, but there's like a significant number of pages dedicated to really talking about entropy and what is it, and like microstates versus macrostates, and different arrangements of energy, and it's pretty confusing, or it was confusing to me at least. And I wouldn't worry too much about all those details. Like, you do want to understand what entropy is fundamentally, being like the way that energy wants to disperse never wants to like concentrate in one place. Um, with the best analogy I can think of being, there's lots of good analogies, but like when you drop food coloring into a glass of water, right? The food coloring spreads through the water. It would never ever on its own all of a sudden just go from being a blue glass of water to being clear water with a single point of blue. Like the food coloring would never go backwards and refocus itself to a single point, because entropy is the driving force that causes things to spread out. That's how things want to. That's what they want to do. Things want to spread out. Energy wants to spread out. Whatever. It all wants to spread out. Um, so that's really the core of what I would try to grasp about entropy. What it is, that's what it is. Don't worry about the microstates, macrostates thing too much. Okay, cool. So then why do we even care about entropy? It's because it turns out it's this really important driving force that basically predicts whether things are going to happen in the first place. And that's important because when we're doing chemistry, we want to know if a reaction's even going to happen or if we need to do something to make it happen, right? If you're like mixing and making stuff, trying to make a new COVID vaccine in a lab, and you have an idea, you're like, oh, I think if we put this with this in a container, then I can make this product, and then we can use that product to make a vaccine. You're going to want to know whether that reaction is going to happen in the first place, or if you should have been heating it the whole time, right? You're going to look like an idiot. You probably wasted $1 billion if you sat there staring at a reaction that's not spontaneous because you didn't bother to figure out if it was spontaneous or not in the first place. So that's kind of like just an idea of what this is all about. And so even the definition of spontaneous can be kind of confusing, I think. I literally have reread this like a dozen times over the years just because I always get a little mixed up. But I think really it's simple. It's just that a spontaneous reaction is one that happens without continuous outside energy being added. It doesn't mean that you won't need to add a little bit of energy, like you might still need to overcome an activation barrier, but once you overcome that process, the reaction will just happen on its own without you sitting there and, adding heat or adding energy or turning a crank or whatever means of adding energy you're talking about. Versus a non-spontaneous reaction would be one that continually needs some kind of outside input, continually needs you to add heat, stir, whatever, something to help it along. Cool. And by figuring out changes in entropy, we can basically predict whether something is spontaneous or whether we had to continuously add energy to it to get it to happen. Okay. So we'll talk about entropy a little more in a second. Some other kind of definitions I think are confusing are like system versus surroundings versus universe. So it almost, the exact definitions, I guess in terms of chemistry, like the system, when they're talking about like find the entropy of the system, it's like the reaction itself. It's like the molecules combining and rearranging to form new molecules, and that's the system. The surroundings are literally everything else aside from the reaction itself. Or maybe you've been told that the system is like the reaction vessel, like the container where the reaction is happening. That's fine too. But just the point is that there's a system, which is a reaction, and the surroundings are everywhere else. All of Earth, all of the solar system, all of the rest of the universe, except for your reaction. So therefore, the universe is then the reaction plus everything around the reaction, right? The universe is everything. So the universe would be your system, the actual reaction, plus everything outside of the reaction. That would create an entire universe. So that's what those, I hope that cleared it up. That's kind of, I feel like I described that weird, but yes, I did not mean to change the slide. So that's what system, surroundings, and universe means. So in terms of entropy, we'll see that the definition of what makes something spontaneous is that the entropy of the universe increases. So even if the system itself becomes like more focused or more concentrated, and the entropy decreases, that can be compensated by the reaction somehow increasing the entropy of the surroundings, like so the outside of the reaction. So if you can create enough entropy outside of the reaction, then you can overcome that decrease in entropy of the reaction itself in order for a reaction to still be spontaneous. And that's why we calculate the delta S of the universe, because that's what determines if something spontaneously happens or not. Okay, next slide. All right, so here are a bunch of entropy formulas. And think this can kind of cause some confusion, like what formula do I use if they ask me to find entropy. So I kind of wrote them all down in one place, and then I'll touch on them real fast. So if you're trying to find the entropy of the system, so the entropy of the actual chemical reaction that's happening, you have these choices here. And which one you use is kind of going to be dictated by what you're given. So if you're given a delta H for the system and you're trying to find the entropy of the system, then you're probably going to use the top equation. If you're given, delta S of the products and delta S of the reactants, then you can use those to find the delta S of the system itself, the whole system. So all of these are different ways to find delta S of the system. Just kind of let the problem guide you. Another way to kind of intuitively check, in case if you're not actually given numbers and you're asked to decide whether the entropy is increasing or decreasing, is that some common ways that lead to increasing entropy would be if one of the reactants in the reaction was a solid, and then it becomes a liquid or forms a liquid later on. That's an increase in entropy. Liquids can move around more than solids. They have more ways to arrange their molecules and arrange the energy. So solid to a liquid is an increase in entropy. Same thing as liquid to a gas. Gases move around more. They can take up more space. They can rearrange themselves in a lot more ways than a liquid can. That's an increase in entropy. And even if you start with a gas and end with a gas, if you increase the number of moles of gas you have along the way, you're also increasing entropy. So these would all be ways that you could tell whether a reaction system is increasing in entropy or not, all with the goal of eventually figuring out if the entropy of the universe increases. Cool. Well, if I jump down to the bottom, the entropy of the universe equation, we can see that yes, it depends on the entropy change of the system, but also the entropy change of the surroundings. So we need to be able to calculate the entropy change in the surroundings also. So there's only one real formula I could find for that, and it's basically the same as the top equation for entropy of the system. It's just that it's negative. The reason why is because any change in energy in the system itself, so in the reaction, is going to lead to an equal but opposite change in energy around it, right? It's basically conservation of energy. If your reaction gives off a bunch of heat, then the surroundings absorb that heat. Or if the reaction requires heat to be added to it, then the surroundings are losing that heat. And so they're directly related, and that's why you can find out the change in entropy of the surroundings based on the change of energy in the system itself. So just the opposite of the delta S system equals enthalpy of the system over temperature, just the opposite number of that. Cool. Okay. So hopefully that didn't just make things more confusing. Hopefully that I just find it helps to kind of put all the equations in one place sometimes and just kind of look at them as a whole. I think that's all I have to say about entropy. All right. So moving on. Gibbs free energy. So this is kind of like the pinnacle of this chapter, the most recent chapter. So we learned about entropy. Why do we care? It's because reactions will occur spontaneously on their own or with minimal outside intervention if the reaction can lead to an increase in entropy of the universe. Sometimes that's not so easy to figure out though. And so what this person named Gibbs figured out is how to kind of combine all these factors into one expression. Delta H minus T delta S gives us this new quantity called Gibbs free energy, delta G. And that's a single value that we can calculate to figure out whether any reaction is spontaneous or not. And so if we look at that equation, delta G equals delta H minus T delta S, and I go back a slide, we can see that it's really very similar to these other equations. Like there's a delta H, there's a T, there's a delta S. We see those here in a couple of different forms. Delta S universe equals delta S system plus delta S surroundings, etc. And that's because this Gibbs free energy equation is literally just a combination of all these other equations put into one nice equation that then allows us to just figure out whether a reaction is spontaneous or not. So it's not anything new. It's just a derivation of all this entropy and delta H and temperature stuff put into one nice little package. And so that's why instead of calculating the entropy changes in the universe to figure out whether a reaction is spontaneous, we can just calculate its Gibbs free energy value. And so what does Gibbs free energy even mean? What's the number mean when we find it? Sometimes that helps to understand too. And what it is we've seen that negative delta G values are spontaneous, means the reaction is spontaneous. The reason being is that negative delta G value is showing that there's excess energy left over after this reaction happens that can then be used to do something else. Basically, there's an abundance of energy, and that's why the reaction was able to happen spontaneously in the first place. There was enough energy present for the reaction to go on, and there's so much, in fact, that there was extra left over at the end. That's what the negative delta G value is. It's how much energy do you have left at the end that you could actually use to do something like power a light bulb or something. A positive delta G value we've seen means that the reaction is non-spontaneous. It does not happen on its own without outside intervention. So that physical number, the delta G positive number, is exactly how much energy we need to add, how much work you would need to do into this system to get that reaction to happen in the first place. So that's what the number actually means. All right, now it's basically the end of my slideshow before we just do some practice problems. But then I wanted to touch on one confusion point, I think, which is that on the chapter about molar solubility, like aqueous ionic equilibrium and solubility constant, whatever, molar solubility is not the same thing as KSP. And that's something that mixes people up, I think. And I remember mixing me up in this class. KSP is an equilibrium constant for a solubility reaction, right? Like say, could be anything like NaCl dissolving to form Na plus and Cl minus. There's some KSP value that tells you how far it dissolves, right? The ratio of products over the ratio of reactants at equilibrium. But oh, go ahead.
You're probably getting to it, but is molar solubility S?
Yes, exactly. Molar solubility is S. It's the S value that you get at the end of the ice table. It's a concentration. It's moles per liter. It's the S value from the ice table. And that tells you the molar solubility, specifically how many moles of something will dissolve in 1 liter of water. And so just be careful with that. Like if she asks you on a test question, what's the molar solubility of blah, blah, blah in this reaction, you're not trying to find KSP. In fact, you'd probably be given KSP. You're trying to find S, and that's the molar solubility.
And that's the solubility constant, right?
KSP is the solubility constant, huh?
What is it? What is KSP? I guess what would you call it?
It's
not KSP.
Solubility constant. Yeah, it's the equilibrium constant for a solubility reaction. So I think you could call it the solubility constant might be what it's referred to as. Yeah, exactly. Yep. So yeah, molar solubility is S. KSP is just like KEQ, it's the ratio of products over reactants. They're related in that you can often find molar solubility from the KSP value, but they're just not the same thing. So just be careful on a test about that. Cool. Does anybody have any questions up to this point before we dive in and just do some practice problems? Very good, very good. Okay, I'm going to close this. And, oh, my desktop is revealed. Don't look. And then let's go here. I'm just kidding, it's fine. There's nothing too crazy on there, hopefully. And then, okay, cool. Let's put this here. All right, so here's the practice exam. And hopefully it's okay with you all if we just go over some questions from the practice exam. I thought that'd be a good way to practice. Dubstep Kitty, that's good stuff. And then, cool. So, in the interest of time, I think I might skip some of these questions and go to what I think are probably the more challenging ones, or just the ones that people expressed interest in going over. Specifically the titration problem. And then we'll go from there. But I'm going to start with the titration problem because those are pretty hard. And if anybody has like a specific problem they want to go over, please throw it in the chat, and then I'll try to figure out how to actually read the chat box at some point but it's not showing up right now. Oh, there it is. Okay, cool. Chat box is empty, so I guess we're good. All right. So, titrations. So we know that we have, where's my little pen? We know that we have 2 variations of titrations, basically. You can titrate a strong thing with another strong thing, so a strong acid with a strong acid base, or a strong base with a strong acid, or you can titrate a strong thing and a weak thing. And the process is a little slightly different, but basically more or less the same. It just helps to kind of figure out at the very beginning what you're dealing with. So on this problem, okay, so it says, okay, so problem 2, 25 milliliter sample of 0.160 molar potassium hydroxide is titrated with 0.250 molar hydrochloric acid. Determine following quantities. A says the initial pH of the potassium hydroxide solution before any acid is added. All right, so before I even tackle that, I'm going to come over here. Okay, what am I dealing with? KOH. I've got my, I think it's open note test, right? So you can have your notes in front of you. And so I would have these written down somewhere, like the 6 strong bases and the 6 strong acids. So this is a strong base. And eventually we're going to be dealing with a strong acid. Okay, cool. So I just like to have that in the back of my head. Strong with strong. And we'll see later why that kind of matters. Okay, so the initial pH of the KOH solution before any acid is added. All right, so if you just didn't even know where to begin on this question, you can kind of work backwards to find your answer sometimes. So they're saying find the initial pH. Okay, well, what is pH? I'm just going to spill everything I know about pH. pH can be found by taking the negative log of the concentration of hydronium. That's one way to find the pH. Another way is that pH equals 14 minus the POH. So when I kind of think about these, I'm like, which one of these is more useful here? Well, I'm finding the pH of a solution that only has base added. There's no acid added, so it's unlikely I'm going to be able to find a concentration of acid and when there's no acid being added at all. So I probably can't even use this method. But I think I can probably use that second method, which is 14 minus the POH. So then what am I missing? Okay, I'm missing the POH. I gotta find the POH. Okay, well, what is POH? POH can be found similarly to pH, except it's the negative log of the concentration of hydroxide. So if I can find the concentration of hydroxide, I can eventually get to the pH. All right, so let's start here. And this is where realizing that I started with a strong base comes in handy. Because what is a strong base? What's a strong base versus a weak base? A strong base completely dissociates. So no matter how much you add to begin with, it all dissociates and you end up with that same amount of OH minus at the end. So it means that we started with 0.160 molar KOH. Once it reacts with water, it all becomes 0.160 molar OH minus. So there we go, there's my concentration of OH minus. So I can then plug that right here, and I would do, so POH equals negative log of 0.160, and I get POH of 0.796. Alright, but I'm not done yet, because they said find the pH, not the POH. So I come over here. I know I can find the pH by doing 14 minus the POH, so I'm going to do 14 minus that number, and I get, pH, come on, pen, where'd you go? pH equals 13.2.
I have a question about the sig figs for pH.
Yeah.
Do you always go to the decimal number of decimal places in your original? I think there was something about that in the lecture. Am I crazy?
No, I think you're right. There's like
Where the decimal places of the original molarity or something? Was that it?
yeah, I'm bad at here and I've gotten lazy with all the sig fig rules over the years, but it's either that or it's that you need one more sig fig in the pH number than you did starting off with. So all our initial numbers have 3 sig figs. So I think you need a 4 sig figs then in a pH value. That might be the rule, or it might be what you said. I'm sorry, I totally can't remember. I can double check, but yeah.
No, I can't remember either. I think it was mentioned in one of the lectures. I don't remember.
Yeah, yeah. Yeah, it might be worth double checking, but there is a funny sig fig rule for pH, and I think it's that you need one additional value, but it could be that you need what you said earlier. But I'm sorry, I'm gonna be kind of lazy with sig figs, which is terrible. I'll try to be right. I'll try to be right with sig figs after this. Okay, but I get 13.2 or 13.20 as my pH. All right, cool. So we got the answer for part A. And if anybody has questions, probably best to just unmute yourself and just feel free to interject since I can't see the chat box. Feel free to just interrupt me anytime. Okay, now I'm gonna erase this.
I think that's what it is. Is it Eva?
Yeah, I just threw in the chat that according to Dr. Google, we start after the decimal point. So if we have 3 sig figs, we'll have 3 numbers after the decimal points, like 13.204.
Okay, awesome, perfect. Thank you for checking that.
Yeah.
All right, very good, very good.
Okay, so number of sig figs equals number of decimal places.
Perfect. So 13.204. Yep. Great. All right. Okay, let's go on to part B. So scroll down. Okay, so part B, I'm going to kind of rewrite our pH that we calculated up there just for reference. So we had pH equals 13.204 from the last problem. All right. Now we're taking our solution and oh, I'm just curious. Have you guys seen like videos of titrations, or have you ever done titrations in a lab? Like, is this totally abstract concept, or is there some visualization happening here when you read this? Okay.
I think our last lab was titration.
Okay, cool. Yeah, exactly. Yeah. Okay. I think it just helps to yeah. I was just checking because I know it helps me to have like a visual idea of what all these words mean. So, okay, cool. Just making sure. All right. So now we're gonna add a little bit of acid to our our original base solution, and then we're going to recalculate the pH. So once you kind of start the actual titration is when you have to change things into moles. So step 1 here is going to be convert to moles, and that's how you kind of simulate what's happening in the reaction on paper. So convert to moles first. So we have, so for base, we've got 25 milliliters times, turn it into liters, so 1,000 milliliters under liters, and then the concentration is 0.160 moles per liter. So we end up with 25 times 0.160 divided by 1,000. All right, so we have 0.004 moles of base, OH minus. All right, now let's do the same thing for acid. Let's figure out how many moles of acid we're adding. So same process, so we have 3 milliliters of acid. Turn milliliters into liters. And the concentration of acid is 0.25. Moles per liter. All right, so we get 3 times 0.25 divided by 1,000. We get 0.00075 moles of H plus, or H3O plus, or whatever you want to call it. Okay, cool. So now we're in moles. I should write moles. Now we can kind of simulate what's happening when we add these things together, because we know that acid and base react. So let's do that. So this is where she uses a BCA situation here. So BCA, and we are simulating the reaction of base with acid, and I'll write out the whole thing actually, of potassium hydroxide with hydrochloric acid to form water and a salt, KCl. Okay, so if we can pause time at the point where we take our beaker of base and then we drip some acid to it, but then we pause time right before the reaction actually happens, is what we write under B. So before the reaction actually happens, we had 0.004 moles of base combining with 0.00075 moles of acid, and then we're imagining that there's no water formed yet and no salt formed yet. The change that's going to occur is that, acid and base are going to neutralize. So you basically subtract the smaller of the two numbers from both numbers. So all the acid's going to get used up because there's less acid than there is base, and then an equivalent amount of base will get reacted away also. To be complete here, technically the same amount of both of these things would form then, right? We don't really care about that too much here, mainly because it's a strong base reacting with a strong acid. So this salt right here has no acid or base properties. We're not forming a conjugate base or a conjugate acid. Neither of these ions can go on to do any reverse reaction. So we actually don't really care about forming KCl in this example. But if this was a strong conjugating with a weak, then we would be forming a conjugate acid or a conjugate base that would be relevant to our overall problem. But in this case, it doesn't really matter that much because it's strong with strong. Cool. And then after they react, there's no acid left. There's 0.00325 moles of base left. And then we have the same number of this stuff here, 0.00075 moles. Cool. All right. So now we've simulated our reaction. So that was like pressing the play button on time, letting time proceed, and the reaction actually happens. And now this is what happened during the reaction. So we have that there's no acid left, and there's a little bit less base left than we started with. They're asking us to find the pH. So I'm going to follow a similar procedure as the last problem, where we found that we can find pH by taking 14 minus the pOH. So I need to find the pOH then in order to be able to do this. Well, I don't have, okay, or let me back up. So what's pOH? Just one more time, it's the negative log of the concentration of hydroxide ions. So now that means, okay, now I need to find the concentration of hydroxide ions. Then I can find pOH, then I can find pH. I'm close to that, but not quite. What I have is the number of moles of OH minus present, but not the concentration of OH minus. So we need to be careful with this. Remember that this chart always has to be done in moles, and that your result is also in moles. It's not molarity. It's not molarity until we divide that number of moles by the volume, right, by liters, to turn it into molarity. So we just need to do one thing to get this to be a concentration, is we're going to take 0.0, let me switch colors. We're going to take our moles of base, so 0.00325 moles of base divided by liters, the number of liters that we have present, in order to end up with a molarity that can then be plugged into our pOH equation. So what's the volume of our solution? Well, we started with 25 milliliters of base, right? but then we also added 3 milliliters of acid. So don't forget to find the total volume at this point in the titration. So it's actually 28 milliliters total present. So that'd be 0.028 liters. Sorry, I was cutting somebody off there for a second. Or maybe maybe not. Okay, cool. So 0.00325 moles divided by 0.028 liters gets you a molarity of 0.11607. All right, cool. Now we have molar. Now we have a concentration of OH minus in moles per liter. Now we can plug that number in here to find our POH. So negative log of that number is, so we have what color should I use now? Pink. POH is equal to 0.93527. But the pH is what the question's asking for. So don't forget to like go all the way through. I remember like stopping at this point, being like, sweet, found the POH, next. But no, finish the problem. So we do 14 minus that number gets us at last to the pH, which is 13.065. And then we can stop and check. Does that number make sense? Okay, well, we came into this problem with a solution of just base that had a pH of 13.204. Then we added a small amount of acid to it, 3 milliliters of not super concentrated acid. So we would expect the pH to decrease a little bit, go towards acidic, and sure enough it did, right? It dropped from 13.2 down to 13.065. And that makes sense. That's what we would expect if we added a little acid to the solution. So that's a good check. We're on the right track. So means we're moving in the right direction. Okay, I'm going to erase. Let me see if I need any of this for the next problem. Oh no. Okay, cool. I'm going to erase this part. How are people feeling up to this point? Okay so far? All right.
Oh, yes. Great.
Cool. Thank you. All right. So part C says, so now we're start talking about the equivalence point. Okay. Quantity of HCl solution required to reach the equivalence point. So equivalence point is defined as the point in the titration where the moles of acid equals the moles of base. Moles here. Moles are important. Talking about moles, not concentration equals concentration, but moles equals moles. Cool. So, and I should clarify, in this case, since we're adding acid to base during our titration, it would be that the moles of acid added during the titration are equal to the moles of base that we started with. So we already calculated the moles of base that we started with in the last problem. It was 0.00, oh, it's right there, right in front of my face. 0.004. So what that means then is that at the equivalence point, since we started with 0.004 moles of OH minus, the point where this titration will reach the equivalence point is when we've added 0.004 moles of acid. So we need to figure out how much of this acid we would need to add to have added 0.004 moles. So we take 0.004 moles over 1. The concentration of the acid we're using was 0.250. 0.250. So we have 0.250 moles per liter. And this will tell us how many liters of this specific HCl solution we need to add to reach equivalence point. So 0.004 divided by 0.25, and we get 0.016 liters. Kind of an ugly number, so better to show that in milliliters, so it'll be 16 milliliters. So that's how much of this acid solution we need to be added to have added the exact amount of acid moles to neutralize the amount of base moles we started with.
Will the pH at the equivalence point, if your salt is neutral, be 7?
Yep, exactly.
But if you don't have a neutral salt, it will not be 7, right? Or if you have other stuff going on, like that's only when it's a strong acid and strong base, right?
Correct. Yeah, exactly. Yep. So for D, the next question here. So yeah, exactly. Anytime you're titrating a strong acid with a strong base or a strong base with a strong acid, the pH at equivalence point is exactly 7. But let's look at the other scenarios real quick, just in case that's not how this test goes. So let's look at why that is. Let me erase this. So
I could go over that part.
yeah, totally.
I feel like that's more confusing than this.
Definitely. Okay, so let's look at this reaction. So here we were doing HCl being added to potassium hydroxide, forming water, and potassium chloride. Okay, so what we just saw is that at the equivalence point is when we've added 0.004 moles of acid to an initial 0.004 moles of base, which then we could look at the stoichiometry and say, cool, well, that would form 0.004 moles of water and also 0.004 moles of KCl, right? Just because it's 1-to-1 to 1 stoichiometry. It's old school. It's like back in the early days of good old Chem 1A. All right, but now it's got a twist. Okay, so we react 0.004 moles of acid with 0.004 moles of base, form 0.004 moles of product, of each product. Yeah, okay. What if we form, though, water? Water is negligible. Well, water itself is pH neutral, so doesn't play a role here. But we also formed KCl. So here's where you have to examine. You say, okay, did I form a substance that's going to affect the pH at equivalence point or not? So anytime you're reacting a strong base with a strong acid, you get a neutral salt that it's not a conjugate base or a conjugate acid. The reason being, the salt is K plus and Cl minus dissolved in water, right? If you try to add OH minus back to this K plus to get back to forming the base, that reaction doesn't happen because KOH is a strong base that only goes the other direction. Same thing for Cl minus, right? It can't grab onto H plus and reform HCl. I mean, it can, but it really barely doesn't really happen in any significant amount. So Cl minus is not a good conjugate base, and K plus is not a good conjugate acid. And that'll always be the case if it's strong, titrated with strong. But let's look at what if these weren't strong and strong? What if it was acetic acid, which is a weak acid, titrating against potassium hydroxide? Acetic acid is whatever, I don't remember. HC2, whatever. It doesn't even matter. Something like that. I think that's right.
Yeah.
All right. So if this was the case, so we're starting with weak acid, we're starting with a tub full of vinegar, and we're dripping potassium hydroxide or any strong base into it to titrate it. Well, now let's think about what happens at the equivalence point. So we could still add equal number of moles of acid to the moles of base present to reach equivalence point. So at equivalence point, we would be, well, so the reaction that happens would form water. The H from the acetic acid would react with the OH from the base. And then we would have we'd have potassium acetate. KH2, what am I saying? It doesn't matter. Okay, cool. Potassium acetate. Okay, so if at equivalence, we added 0.004 moles of acid to neutralize 0.004 moles of base, and we formed 0.004 moles, starting to mix my words up, of acetate, potassium acetate. Well, now, that's not irrelevant. That matters now, because the pH is not 7 at the equivalence point, because we've formed a very small amount, but a significant amount of a base, right? C2H3O2 minus the conjugate base of what started off as a weak acid, and the conjugate base of a weak acid is always itself a weak base. So we don't have a neutral solution. We actually have a solution where the acid that we started with has been neutralized by base being added, but in the process we've formed some weak base. So we actually have a slightly basic solution at equivalence point in this case. So the pH would be slightly over 7 because of this conjugate base that we formed during our titration affects the pH. And then the opposite would be true if we were titrating a weak base with a strong acid. You would end up with a little bit of conjugate acid present at equivalence point, which would make the pH slightly acidic.
So for this one, is there going to be the OH groups and the hydronium ions that are out there? Did I phrase that badly?
Like at equivalence point?
Never mind.
Okay.
I don't think I know.
At the actual equivalence point, this would be the only base present.
Okay.
So to find the pH, if you were asked to find the pH at equivalence point of this solution, I think, without spending too much time thinking about it, I think you'd have to do an ice table based on the Kb value of acetic acid, which you would find from the Ka value of acetic acid, which is in your textbook. And then you do an ice table to find the concentration of OH minus that was formed as a result of this conjugate base being present. So that's one step where doing a titration of a strong acid with a strong base is less work than doing a titration of a weak something with a strong something. Fewer ice tables need to be done when it's strong and strong. So if you notice from the get-go on your test that you have a strong titrated with a strong, then breathe a sigh of relief for a second because it's a little less work for you. All right, cool. All right, I'm going to move on to E. Okay. So part E says the pH of the solution after 20 milliliters of HCl is added. So we can basically do the same step as when we did B. It's no different. If memory serves. Yeah, it should be the same. So we'll just really follow the same steps. Maybe I'll abbreviate it too, since we kind of already did part B. But you would just turn it into moles first. So we know that 0.004 moles of base is what we started with. So I need to drink some water. And then we would calculate how many moles of acid we're adding to the solution as a result of this 20 milliliters. So 20 milliliters, 1,000 milliliters in a liter, and then 0.250 moles per liter was the concentration of HCl. So we get 20 times 0.25 equals, divided by 1,000, 0.005 moles of acid now we're adding. So the difference here is that we're now going to overwhelm the amount of base present um, with this amount of acid. We're adding more acid than there is base. So if we come over here and do our reaction, and so one trick I think for this is don't look at this question and think of it like linearly. Don't be like, okay, we're already at the equivalence point. Okay, what happened? What's my pH at the equivalence? Like, oh, what happens now? I don't know. You basically just start from the beginning again. You start as if this were the first thing you did. You took a plain base solution and you added 20 milliliters of acid. Find the pH exactly the same way you did in part B. So we have KOH reacting with HCl, forming stuff that we don't care about for this problem. Before BCA, right? Yeah, BCA. So we have, before the reaction happens, we have that 0.004 moles of base that we started with, but now we're reacting with 0.005 moles of acid. Change, now we subtract the smaller number, which now is the base. So minus 0.004, minus 0.004, all the base is gone, and we have 0.001 moles of acid left. We need to turn that into a concentration. So 0.001 moles divided by now the total volume. We've added 20 milliliters of acid to the original 25 milliliters of base, so 45 milliliters total. 45 milliliters, but it needs to be liters because we're trying to find molarity. So that's moles of acid over 0.045 liters. That's going to give you your concentration of H+, aka H3O+, and then you just take the negative log of that number to find the pH. And if it's okay, I won't do all the calculations because I think you guys got that part, or at least it's very similar to part B. Except that now we don't need to find the POH first and then find the pH. We can just find the pH straight away because the base is gone. All we have left is acid anyways. Cool. Alright, let's clear this. Man, is that titration? Ooh, it's done. That's a long problem. Alright. Let's see. Okay, what else we got? Does anybody have any preferences on the next? Because I don't have too much more time, but we could probably try to tackle one more problem. I'm going to look at the chat box for a second in case anybody replies. But if anybody wants to make a request, now's the time. Or I'll just pick a challenging one. Let's see. Oh, buffers. I know people expressed interest in like talking about buffers, so I could just do this buffer problem. Okay, I see some heads nodding. Let's just do that.
I'm nodding my head. My video.
All right, cool. All right, buffers. So, what's a buffer? A buffer is just a solution, so a glass of water or whatever, beaker of liquid that has both an acid present and its conjugate base present at the same time. That's it. Okay, so here we're creating a buffer by combining some amount of methylamine, which is going to be a base because NH3 is a base, and then we're also adding some of its conjugate acid, CH3NH4 plus. It's got that extra hydrogen on there that's going to get released. That's what makes it an acid. So we've got a base along with its conjugate acid, so just a base with a proton added to it. We combine a certain amount of both of them into a container, and now we have a buffer. Cool. So they say calculate the pH of this buffer. Okay, so the cool thing about buffers is that we have the I always think it's called the it's not called the David Hasselhoff equation, but that's like how I ingrained it into myself, but it's called the Henderson-Hasselbalch equation. But I prefer David Hasselhoff equation. Okay, so it looks like this. The pH of a buffer solution is equal to the pKa plus, oh, I better double check this. I thought I had it memorized, but I'm pretty sure this is right. Plus the log of the concentration of base divided by the concentration of acid.
This only applies to buffers, correct?
It does, yes. It does only apply to buffers. The good thing is that it also comes into play when you're doing titrations. Specifically, titrations that are not like the one we just did, so not where it's strong titrated with strong, but titrations where it's strong titrated with weak, it comes into play for the same reason that we were kind of examining earlier, where during the titration, you start to form conjugate base or conjugate acid. So very quickly, early on in the titration, you've actually created a buffer, and so you can kind of cheat sometimes. Instead of doing an ice table to find the pH during a strong weak titration, once you know you have a buffer because you've created some conjugate base or acid, you can use this equation to find the pH in the middle of your titration.
But if it's weak, like weak acid is the weak base, this wouldn't apply, correct?
It still would apply. I think it still could apply because you would still be forming a buffer.
So but I'm confused. So anytime you have something weak, it always makes a buffer. Or no? Is that the wrong way of thinking? I'm sorry if I'm asking too many questions.
No, it's okay. It's okay. I don't think you'll be asked to do I could be wrong about this, but I'm pretty sure you won't be asked to do a weak titration. It'll be either strong or strong weak. And so, I'm gonna show you real quick. So like kind of what we saw earlier, right? So if you were say titrating, what did I say? Acetic acid, HC2O3, H. It doesn't look right. Whatever. With H. Damn. 5, 6. Doesn't matter. Okay. With strong. So weak acid with strong base. So weak acid, strong base. So initially, you would just have a weak acid solution, right? You would start off with weak acid. If you wanted to find the pH of that weak acid solution, you'd have to do an ice table, just like always. Anytime you want to find the pH of a weak acid, you got to do an ice table, because there's only weak acid present at first. But once you start titrating with your strong base, you start to form the products, right? So you start to form water and potassium acetate, but I'm going to leave off the potassium part because it's not important here. So water and acetate. Oh, there it is. Just gotta let it flow sometimes. Okay. Cool. So from the moment you add a single mole, a single millimole or whatever of strong base, so as soon as you start your titration, you're now causing this reaction to happen, right? So let's imagine that we started off with some imaginary number, 0.5 moles of acid. That's how much we started with. And then we added 0.1 moles of base. So we would do our little table. This would neutralize, right? This would decrease by 0.1, so it would go down to 0.4. But in the process, we would form 0.1 of this, moles of this, and 0.1 moles of this. And so from the moment you start your titration, you've now formed a buffer. Regardless of how good of a buffer it is, you have a buffer. You have a weak acid present. We have 0.4 moles of weak acid present. And its conjugate weak base present, 0.1 moles of it. So in a strong weak titration, you pretty much instantly have a buffer as soon as your titration starts. Just not initially, when you're just looking at the acid or just looking at the base. There's no buffer there. But as soon as the titration starts, you formed a buffer, and then you can start to use the Henderson-Hasselbalch equation to find the pH as you go along. Does that clear it up a little bit? So that's how this would apply to titrations. I'm hoping it's a good omen that she gave you the strong on the practice test. So hopefully you get strong on the exam too. I don't know. I didn't get to ask anybody like if her actual exam was reflective of the first practice test. Was it? Or was the exam a lot different than the practice test?
I feel like they've always been pretty close.
Okay, that's good. That's good. Cool. All right. So we want to find the pH of this buffer. We have, 0.15. Okay, cool. So we have a Kb value, so that's kind of a problem. Henderson-Hasselbalch equation uses pKa, but it's not really that big of a problem because we can find the pKb by taking by taking the negative log of this, so negative log of KB gives you the PKB. And then if I'm hopefully right about this, I'm pretty sure pKa plus pKb equals something. Is it equal 14? Jeez Louise. Let me check. pKa plus pKb. Yeah, 14. Okay, cool. So, cool. So here's how I would trace this out, right? Sorry, I kind of did this in my head, but so I know I can use the Henderson-Hasselbalch equation to find the pH of the solution. That is pKa plus log of base over acid. Cool. Unfortunately, I am given the concentration of acid and the concentration of base and the concentration of acid, but I'm given a Kb value, which is not even a pKb value. It's a Kb value. So remember that just like how pH comes from taking the negative log of the H3O concentration, you can do the same thing to Kb values and Ka values to create what's called a pKb or a pKa. The little p literally means taking the negative log of something. So pKb is the negative log of the Kb. And then we can get to the pKa from that. So let's do that. So we do negative log of 4.37 times 10 to the negative fourth. Okay, so I get pKb of 3.3595. And then if I want to find the pKa, subtract pKb from both sides of this equation. So I have pKa equals 14 minus pKb, which we found to be 3.3595. So I do 14 minus that number, and I get a pKa 10.64. I'm just going to leave it at that. Maybe I should do a little more sig figs. 0.05. All right, now we can finally use the Henderson-Hasselbalch equation. So we're going to go pH equals pKa, so 10.6405 plus the log of base. Where's the base? Right there. 0.15 molar divided by concentration of acid in our buffer, which is 0.20. And what we get is, let's see, this number plus the log of 0.15 divided by 0.2. I got 10.516. Oh, we only need 2 sig figs here, so 10.52. And hopefully that's what she got on the answer sheet. Let me check. Where did that go? Don't want to be doing the wrong things here. Whoa, that's hard to look at. Okay, let's see. Which problem are we on? Yeah, 10.516. Okay, cool. So 10.52, 10.516, sure. Close enough. Great. And then one note about the Henderson-Hasselbalch equation is that you can actually use the molarity, or you can use the number of moles you have. It doesn't matter when you plug it in, because moles per liter divided by moles per liter, the liters cancel. So really you're just doing moles divided by moles anyways. So you can put moles or molarity into this ratio here, the log, in case that ever comes up. Because you'll notice if you look at how she solved this problem, she put moles in there. That's because we're going to need that in the next part of the problem, so she's kind of anticipating ahead. But you can use the other one. All right, so that's how you use the Henderson-Hasselbalch equation. It's really fairly straightforward usually. Here we just had to kind of find it in a roundabout way because we started with a Kb, and we needed to get to pKa. All right, let's see what the next part says. And I'm so sorry to do this, but I have to leave in 5 minutes, so we'll just kind of plow through a little bit more. And I gotta bounce. Okay, so we have pH of 10.52. Oh, I should have kept that other number up there. Whatever. pH 10.52. And then, okay, how many grams of NaOH would need to be added to raise the pH of this buffer to 11? So this is a challenging one. Okay, where do we even start? So, okay, so we're trying to raise the pH. So we know we need to get a little more base in there and get rid of a little bit of acid. Okay, I wish I hadn't erased my pKa value. I'm gonna recalculate it, but unless somebody remembers what it was. Does anybody remember what the pKa was? If you do, just type in the chat. If not, I'll just recalculate it. Anywho, here's how we're gonna do this. Oh, thank you.
10.6405.
Thank you. 10.6405. Okay, pKa. Okay, sweet. So here's how you solve this kind of problem. So if you're ever asked to make a change to a buffer, like figure out like how you need to shift the acid-base ratio to change the pH of a buffer, you can still use the Henderson-Hasselbalch equation. So try to remember that you can use this kind of in multiple ways. It's really being used in the same way, just solving for a different variable. So we saw the Henderson-Hasselbalch equation was pH equals pKa plus log base over acid. All right, so now we're kind of solving it in a different way. So we still have a pKa that works here. Now they're giving us a new pH to try. So we're just going to plug that pH in here. So they're saying, basically what they're saying is, how would you adjust this ratio, the base to acid ratio, in order to end up with a pH that was 11? So we can just do that. Okay, let's just make the pH 11 in the Henderson-Hasselbalch equation and then kind of solve for that ratio, the new ratio, to see how we need to fix it. So we say, okay, cool. They want the pH to be 11. We know the Henderson-Hasselbalch equation says pH is equal to pKa 10.6405 plus the log of, so here, I'm trying to think if it matters whether we use the concentration or the moles. Let's try with the molarity first. So 0.15, yeah, I think that'll work. So 0.15 over 0.2, 0.15 over 0.2. Oh, I see why it'll matter. Okay, it's fine. But we don't actually want that to be our ratio, right? We know we need to tweak this ratio. So we actually we want to increase the amount of base present because we're trying to raise the pH from 10.5 up to 11. And you increase the pH by increasing the amount of base. And conversely then, we're going to reduce the amount of acid present. One goes up, the other goes down. And now it's a matter of the algebra. So let's solve for this x. So first thing is I'm going to subtract 10.6405 from both sides. So we have 11 minus 10.6405. Okay, so I got 0.3595 equal to the log of this thing here, 0.2 minus x. Okay, so to get x by itself, we gotta get rid of the log. So to get rid of a log, you do 10 to the power of that thing. So you gotta do that to both sides. So on the left side, we get 10 to the power of 0.3595. And that is, where's my red? I'm gonna come over here, 2.2882 is equal to, the 10 to the power of log just makes the log go away. So it's just equal to what's inside the parentheses. So 0.15 plus x over 0.2 minus x. And meh. Okay, so now we gotta isolate x, so multiply by 0.2 minus x over here. Do the same thing over here. Okay, so 0.2 times 2.2882. So we have 0.45764 minus 2.2882x. So I kind of just distributed this times this times this. Equals 0.15 plus x. Cool, we're almost there. Okay, so I'm gonna subtract 0.15. The whole goal is to get x by itself, right? So let's get rid of this 0.15 on both sides. So minus 0.15, 0.30764 minus 2.2882x equals x. Now we just need to combine those x terms. So add this x term to both sides. So 1x plus 2.2882x is 3.2882x's. Cool, so we get 0.30764 equals 3.2882x. And the last thing is divide by this, 3.2882, to finally find x, 3.2882. Okay, so that number divided by 3.2882, and I get x equals 0.09356. 0.9356. Phew. Alright. Okay. So now the question said how many grams of NaOH will we need to add? Okay. Well, now we know. What do we know? Yikes. Okay. So now we gotta figure out. Okay, so we figured out x. So that's how many like moles per liter, because I started off in concentration over here. So that's how many moles per liter we need to add. So we can just combine those now. So go back to our original kind of place. So 0.15 plus x would give us okay, so when we add x over here to the base that we started with, we can now see that we want 0.24. I hope I didn't mess this up by not converting to moles to start with, but I guess we'll just see how it works out at the end. I'm not 100% sure if this is gonna work, but we'll find out soon. Okay, so that's our new concentration of, oh, I didn't do that right. That's our new concentration of OH that we want. We want to be this concentrated in OH minus. Well, in base. In conjugate base. To get the pH to be 11. Alright, you guys still with me? Okay. Let's figure out how to do that. And hopefully I didn't mess this up. Okay. I'm going to erase some of this work here. Alright, so if we want to have... Oh man, my writing's getting real sloppy too. Okay. So if we want a concentration of base to be equal to 0.24355 moles per liter. How many grams of NaOH do we need to add to do that? So, okay, so good question. Okay, so let's figure out how many. Dang. Okay, let me think about this for a second. Okay, so 150 milliliters of 0.15 molar. So that would be, okay.
We multiply by A mu.
Yeah, definitely at some point over here for sure. Yeah. Okay, let's try. Okay, so if we have this many moles per liter. Oh, you know what? We don't need to do to the whole number. We're trying to figure out just how many we need to add. And this is how many we need to add. So I think actually we just need to calculate based on this X number. So I think they're saying how much would you need to add to the existing buffer to raise the pH.
And would we have needed to start in moles though?
That's my fear, but I'm not willing to give in yet. I'm gonna keep I'm trying this for one more second.
Okay, I'm sorry.
No, it's okay. If that's the case though, it would be the same process. It just would have had to change it to moles to begin with. But I was feeling good about this, but honestly I'm kind of winging it here. But let's see if it works. Okay, so let's say, we need to increase by 0.09, this is our X value, 356 moles per liter. That's how much we need to add. Oh, I should have written that like a normal person, moles per liter. And then our concentration that we're working with is 0.15 molar. 0.15 molar. So 0.15 moles per liter. And then grams per mole. No, I give up. I don't want to try anymore with the molarity. I think I should have switched it to moles at the beginning, like people have mentioned and like I feared. So, unless somebody figured this out, I'm starting to go brain dead. Okay, so let's I'm not gonna redo the whole problem, but it's the same idea. Okay, so like instead of having put the molarities here, it looks like I should have converted to moles first, because I'm struggling to figure out how to get out of the place I'm in. So if we had put moles here to begin with, you would have just calculated the moles from the start. So you would have said, okay, we have 150 mLs, right, of 0.15 moles per liter. Convert mLs to liters.
Well, could you do the reverse of that?
I feel like you could. I feel like you...
If the reaction, if the balanced reaction is like, couldn't you calculate the ml from the mole? No, I don't know if I'm asking that right.
I think there is a way to continue with the way I was doing it, but I'm not seeing it right away, and I don't want to waste your guys' time sitting here trying to solve my own weird ways of doing things. So let's just go with this. So it should have been converted to moles first, it looks like. Why? I don't know. How are you supposed to know that? I'm not totally sure. I think there was a way to actually solve it the other way, but I'm not seeing it right now. So I guess just mental note, if you come across this problem on the test, change it to moles first. Don't start with the concentration. Up here in the part A, it didn't matter whether we use concentration or moles, you would get the same answer, but in part B, apparently, it seems to matter, maybe. I don't know. But yeah. So just instead change these numbers to moles, and then you just follow the exact same process. You solve for X, and then it'd be real easy because X would be the number of moles of base you need to add to get the pH up. And we know that the molar mass is the conversion from moles to grams. So you would just calculate the molar mass of sodium hydroxide, and that will let you convert from moles to grams. And that would be how many grams of sodium hydroxide you needed to add to get the pH up.
Yeah, we got the answer key, so we can also verify that we got the correct answer using the method.
Okay, cool. Right on. All right. That's all I got time for. Thanks everybody for being here. So I don't have time to go over more. Hopefully I knew I wouldn't have time to go over like really any entropy problems, so I tried to address some of that stuff early. But hopefully this helps with the titrations a little bit. So I know those are tricky. For sure.
This exam's gonna be as long as the practice exam because
Takes a
I don't know
while,
if anyone-
right?
I don't know if anyone else is worried about not being able to finish.
Yeah, 2 hours is pretty tight, I think.
Yeah, especially because I feel like some of the ice table ones, like when you have multiple ice tables, take like it's like a lot of writing and it takes a long time.
Definitely a lot of writing. Yeah. If I were studying for this test, I would probably do this practice test like once, kind of with the aid of the key, just to get around ones that I couldn't figure out, and then do it like 2 more times without the key. Yeah. Just do it a few times until you can do it without the key, and then you'll know you know it pretty well enough.